Hello, class. Welcome, 388. It's good to see all of your bright, smiling faces here today. My name is Steven, and I am going to go over the prerequisites for this class, mostly what you need to know, most importantly, from 378, and a little bit of linear algebra 2 to prepare you for problem set 0 and the associated problems. So here's what we'll start with. In 378, you had okay, well, hopefully off to a great start. Okay, in 378, you had some thing that you call a probability distribution function. Okay, f of x. So we'll call that a PDF, probability distribution function. And a discrete one would look like some values. You get, probability is 0.6. If x is 0, it's 0.3. If x is 1, it's 0.1 if x equals 2. Right? So you have some distribution of probabilities, and it's discrete because it can take on a discrete number of values, 0, 1, or 2, and has a certain probability. And you can see all the probabilities add up to 1. That's what makes a valid PDF. Now, if you had a continuous probability distribution function, it would look more like you would have some function. Close this door. You'd have some function would be the probability of x if x was in some interval, let's say from a to b, right? But if x is not in that interval, then your probability would be 0. And if I were to graph this, show you kind of what it would look like. Let's say you had some interval from a to b, and you had some, function that maybe looked like that. And really, you just get that part of your function, and then all of the area underneath your function would integrate to 1 to make it a valid CDF, okay? And it would be 0 all other places, so it's only valid in this integral. So that's what a continuous PDF would look like. And in continuous land, if I were to ask you the probability of any discrete value, like what's the probability that your random variable x is exactly 2.176, that would be meaningless, right? That probability is like 0. So we talk about integrating over ranges of probabilities to understand what the probability of that range actually is. So I could make another graph where I follow the journey of integrating over this function. And at a, it should start at 0. And then, as I continually get more slices of this probability, it would go up and up and up. And then, it looks like with this one, it would taper off. And by the time it hit b, it should equal 1, because we've integrated over our entire function, then it's 1 forever. So this right here is called a CDF, a cumulative distribution function, and it shows what happens when we integrate over a PDF. So a CDF would be the integral of our PDF, which I'll call f of x, okay? So that is a CDF, which usually would be the capital F of x, is how we would denote that. And you don't have to have a probability distribution function in terms of just one random variable. You could have it in terms of 2 random variables, like f of xy. That could be a joint PDF, joint probability distribution function. And so you could get, you could split that up by summing over all of your, whether in discrete land or continuous land, you could sum over all of one variable to get your marginal distribution function in terms of the other variable. And so if I summed over all of my y's, it would give me my marginal distribution for x. It would be integrating over that function with respect to y, and now I get the marginal distribution for x. So this is a marginal distribution function. We put the x there to just make it super clear that that is marginal distribution of x. And joint distribution function, cumulative, all of that. If I were to talk about summing over some part of this function, because that's what a CDF gives us really, is some function where I can plug in a number for x, and that'll give me the probability all up to that point, right? So let's say my x is here that I choose, I'll call it C, right? Then, I'll get that area for my PDF. So let's say that's 0.8. So I would have chosen the 80th percentile of my function, right? This point right here, C, that is the 80th percentile. If I were to choose this number right here, let's call that C2, and get the 50th percentile, the 50th percentile would be the median, okay? So that's all the median is. It's where your CDF equals 0.5. So that's the only definition of a median. And in this case, our function is symmetric, therefore the median will be in the middle and the same as the mean. Okay, so that's probability distribution functions and all that stuff. That should be a review of 378 for you. Anything else I want to say about that? Nope, I think we're good. Okay, let's see if this will erase. All right, someone did something with this board. These things do not erase now. So, apologies for whoever broke the board in Westview 1144. Holy cow. Gonna have to be good enough. Anyway, we're in blue. Surely that won't cause any problems. Okay, so other things that you should know are expected value, covariance, variance, all those formulas. So if I were to take the expected, no, that's a great place to write that actually. If I were to take the expected value of x, in discrete land, it would be the sum. I would sum over all of my numbers of x, however many x I had, so I equals 1 to n, and I would sum over all of my x's weighted by the probability of observing that particular x, okay? So sum of all my x's times the probability of observing that x. And in continuous land, it's going to be the same thing, all right? The expected value of x is going to be the, I can't do a discrete sum, I have to do a continuous sum with an integral. So, holy cow. With that integral, I'm going to sum over all of my x's times the probability of observing that x, which is going to be given, remember, by the integral over that range of the function. Okay, so I'm going to integrate over everything, x times the probability of observing that x. So same thing, right? We're doing the same thing in both of these cases for expected value. And it's similar for covariance and variance. So the covariance of two variables x and y is going to be expected xy minus expected x, expected y. Okay, so similarly over here, the expected value, the covariance of xy is going to be continuously the expected value of xy, so integral xy f of xy, oh, there should be a dx up here. And this is actually double integral because you're summing over two variables, okay? So that's dy dx right there, okay? Minus expected x, expected y. Okay, so that's your covariance, all right? It's the same, you're just using the expected value from here. And variance is a special case where you take the covariance of one variable. So the variance of x is the covariance of x and x, and that is going to be expected x times x minus expected x, like so. Okay, so therefore variance of x is going to be expected x squared, so here's your x squared times the probability of observing that x dx minus expected x, hopefully I'm writing all of this right, squared. Okay, so that's expected value, covariance, variance for discrete and for continuous functions. Okay, so let's see. So to put this into perspective of when we're going to use discrete, when we're going to use continuous, mostly. Let's talk about how when we collect data, we have some sample of our data, right? So let's say I'm looking at the population of people and their ice cream consumption. So this is ice cream consumption. And let's say that there is some true gospel truth about everyone's ice cream consumption in the population, absolutely everyone. And we don't know this gospel truth, but maybe it's something like, some amount of people consume 0 ice cream, and maybe it goes up a little bit and peaks at a certain value and then goes down like that or something. Okay, so this is some continuous function representing the population ice cream consumption. Okay, so and we'll call this x for our random variable. Okay, so this population is going to have some mu, which is the expected value of this function. All right, and it's going to have some variance. It's going to have some sigma squared. We'll call that the variance. So mu and sigma squared are unknowable, unobservable things, right? We don't know these values for the entire population. I'll call those unknowables theta, okay? Because they're Greek letters, and just like the real Greeks, we will never know them. Okay, so you got theta up there, and it represents things like mu and like sigma squared. Okay, mean and variance. But then we have estimators for those variables. We'll call those theta hat. These estimators are how we try to estimate the variables. Okay, so I can have some. Let's say I collect a sample, and I have some sample of people where I'm trying to get an idea about the population. So let's say my sample looks like this. Okay? So notice that I've collected a sample and I have a finite discrete number of people that I've collected in the sample, right? Some finite dots right here. So this is also going to have some sample mean. I'll call that x bar. And it's going to have some sample standard deviation. We'll call that s squared. Okay? So x bar, I'm going to use as an estimator for mu. Okay? And s squared, which comes from my sample, I'm going to use an estimator for sigma squared. Okay? So that's how those relate. Now, x bar, my random variable, the sample mean of my random variables, that actually also has its own distribution, right? If I were to take like many samples, then I would get an x bar for sample 1 and an x bar for sample 2, and an x bar would be noted like this, right? It's just the expected value of a discrete sample, except my probabilities, since I don't know the probability of observing every one of these, I'm just going to assume they're all the same probability. So it would be very similar to that, except it would be, I'm just going to say 1 over n times the sum of all my x's, okay? That's what I'm going to call x bar. So really I'm just giving all of those the same probability. All right, so, but x bar has its own distribution, and that distribution, we know some things about it. As my sample size goes to infinity, what I know from something called the law of large numbers is that that is going to be centered around my true population value, okay? So the bigger my sample size is, the more confident I am that x bar, its distribution, if I were to take more and more samples, is going to be centered around this. And also as n goes to infinity, I know by something called the central limit theorem that the distribution of x bar is going to be normal, okay? So it's going to be approximately normal by the central limit theorem, and it's going to be centered around the true population mean by the law of large numbers, and that's more true the closer that my sample size is to infinity. Okay, so those are some things we know about data, and that's why we would use these different formulas for discrete and for continuous. That's when those would come into play. Let's see. So we talked about the population, we talked about samples, estimated distributions. Yes, and so we use, because of the law of large numbers and because of the central limit theorem, because of what those things tell us about our estimator, then we can actually make estimates and predictions for what this population actually looks like, what the population mean is, and what the variance is sometimes as well. And we do that with confidence intervals and with hypothesis tests. Confidence intervals, we take, knowing the distribution of x bar, we say, okay, we are going to take what we get in our sample, our x bar that we get, and it's going to be plus or minus some margin of error, and that's a confidence interval, right? Then a hypothesis test is where you have some null hypothesis, call that H null. You say, okay, I'm going to say the null hypothesis is that the true population mean is going to be something, okay, 6. And then the alternative hypothesis is going to be that mu is, you could say not equal to 6 if you want a two-tailed test, or you could say, maybe less than 6 if you want a one-tailed test. But hypothesis tests are based off of what really affects these things, both of these things actually, is your standard errors. The standard error is the really just the standard deviation of your estimator. So there's some standard deviation of x bar, sigma squared of x bar, we'll call it, okay? And that, in reality, is just sigma squared over your sample size, right? That is what the standard deviation of x bar is. So we'll call that the standard error because it's corrected by your sample size and it's the standard deviation of your estimator. So some sigma squared of x bar, and of course we don't know that, so we estimate it with our sample, and we estimate it with s squared corrected by our sample size. Okay, so standard errors are very important in our data for making hypothesis tests. If you have a small data set, typically you'll have very large standard errors and you won't be able to make very good predictions. But if you have a very large data set, then your standard errors will be smaller and you'll be able to make tighter predictions. Okay? I talked about s squared here. Let me go a little bit more into that because s squared, you might think that we would try to get that variance, that we would estimate it with the sum of, with 1 over n, the sum of, and this is another way to write our variance, but xi minus x bar squared, right? From I equals 1 to n. That's very understandable, but that's actually not what we do for s squared. We actually do 1 over n minus 1. And the reason we do that is because if we were to use 1 over n and calculate this out, we would find that that estimator is actually biased. I'll call s squared the 1 over n case, and let's say that the 1 over n minus 1 case. Let's say that the 1 over n case, let's call that 1 sigma hat squared for now. So we don't get confused. Let me tell you what I mean by it's biased, okay? Bias means when we're estimating something, if something is unbiased, then the expected value of our estimator is going to be the true value, right? Okay, that is something that's unbiased. But we might find, in some cases, that the expected value of whatever estimator we're using, if we have a biased estimator, is that it's actually the true value offset by some bias, okay? Which is bad, okay? We don't really want that. And in this particular case, we know that sigma hat squared is actually biased, right? The expected value of sigma hat squared is what is that? I think it's n minus 1 over n times sigma squared, which gives us, if we were to multiply that out, n over n sigma squared, which is sigma squared minus 1 over n sigma squared. So that's the expected value if we were to actually do all the calculations. So that's not great because that's a sigma, not an 8. Because that's what we want, but then we have this bias right here, okay? So we have just found the bias of sigma hat squared. It's negative 1 over n sigma squared, okay? So it's a biased estimator. But there's something that's close, almost as good as being unbiased, not quite as good, but it's called consistency. And consistency is when consistency has to do with as your sample size gets larger. Once again, that's another principle that's going to come into play a lot. So as your n goes to infinity, this is what happens with consistency. Because with bias, we have some true value over here, right? We have mu, but we see that, the distribution of our estimator is actually going to be not the true value. It's, the true value minus some bias, okay? So we would call this downward biased because it's centered around some value that's under the true mean, okay? But if we were to take larger and larger samples of, with the estimator sigma hat squared, we would find that it would be closer and closer and closer and ultimately converge around the true value. I'm using mu here, I probably shouldn't, but just ignore the mu part. But there's just some true value right here, okay? Call it theta. Right, so as we took larger and larger samples, we would find that it actually would get closer and closer to the true value. And so we call that consistency. Okay, consistency, and then it actually would converge as n goes to infinity completely on the true value. So not only would the bias go to 0, but the variance would also go to 0. And that is what consistency is. Then the bias and variance go to 0 as n goes to infinity. Okay? So sigma hat squared is a consistent estimator, but you know what? S squared is actually an unbiased estimator. So we use that one instead. Okay? So very important that concept of bias is going to come up lots in this class. Okay, we talked about bias, consistency. Efficiency is another term for estimators. That is a relative term. A more efficient estimator is an estimator with a lower variance. Okay, so more efficient means lower variance. All right, so that's all I want to say about that. Okay, let's see if we can erase this board. This is not good. What happened? I used this literally like a week ago. It was fine. Somebody's going to be very mad if they try to teach a class in here. Okay, well, let's call that good enough. Wow, that looks awful. Okay, let's talk about just basic rules of expected value and covariance and variance, because you should know those things too. So let's take the expected value I will take of, wow. How about 3xy minus 2y plus 7? Okay? So if you were to take the expected value of these things, it's pretty simple. You would just take the expected value of each of them, right? So expected value of 3xy minus expected value of 2y plus the expected value of 7. Well, we expect 7 to just be 7, right? And you can pull these constants out. This would be 3 expected value of xy minus 2 expected value of y plus 7. Okay, that's how our expected value works. Let's take the covariance of, you need the covariance of two things. So let's take the covariance of 3xy and negative 2y plus 7. Why not? All right, so the covariance of those is the covariance of 3xy and negative 2y, and then you distribute it to the 7 as well. So plus the covariance of 3xy and 7. Okay, plus, now you actually need, did I do this right? Covariance 3xy and negative 2y plus covariance of 3xy and 7 plus 2 times the covariance of, oh, no, I'm thinking of variance. Never mind. We're good. Okay, so there's the covariance of 3xy and negative 2y and the covariance of 3xy and 7. Now you can pull these constants out of covariance as well, just like with the expected value. So this is going to be 3 times the covariance of xy, I'll do the negative 2. Negative 2 times 3 times the covariance of xy and y, plus, and then the covariance, well, 7 actually doesn't vary, so the covariance of something in a constant is 0. So it's actually just going to be that. Okay, is that right? Looks right. Okay, now we'll do the variance for last. So the variance of 3xy minus 2y plus 7 is going to be equal to, okay, so this is where this comes into play. So it's the variance of each of these things, the variance of 3xy minus the variance, plus the variance of negative 2y, plus the variance of 7. And now for each of these terms I need to do a covariance. So it's 2 times the covariance of 3xy and negative 2y plus 2 times the covariance of 3xy and 7 plus 2 times the covariance of negative 2y and 7. Okay? Well, thankfully, something covariant with a constant just goes to 0, so we can not worry about those. We just need to do those. So when you pull something out of a variance, you actually have to square that constant. So it's going to be 9 times the variance of xy plus 4 variance of y, and the 7 doesn't vary, so the variance is 0, plus 2 times the covariance, and then we'll actually pull out the 3 and the negative 2, 2 times 3 times negative 2, covariance of x, y, and y. Okay, so just knowing those rules for expected value, covariance, and variance will help you a good bit, because we're going to be doing some of that stuff. Okay. Now, lastly, I'll make a couple comments on vectors, linear algebra stuff. It's actually, we're not going to go super deep into anything linear algebra. I'll just go over some basics. Okay. All right, so this love it. So this is a vector. 1, 2, 3. Doesn't have to be 1, 2, 3. I'm not creative with my numbers. So that's a vector. All right, it's called a vector because it's a skinny matrix. It's also a matrix, I guess, but a matrix has more columns. So it's like 1, 2, 4, 7, 3, 9, something like that. All right, so we'll call this vector A, call this matrix B. Why not? So these we can refer to by their dimensions, which is the number of rows cross the number of columns. Okay, so A we would call a 3 by 1 vector. Okay, and B we would call a 3 by 2 matrix. Okay, there you go, 3 by 1 and a 3 by 2. Now the transpose of a vector is where you basically just lay it on its side. All right, it's the same thing, but you just turn the row into a column, or vice versa. So A transpose, I'll denote by that apostrophe, is going to be 1, 2, 3. There you go. That's A transpose. It is a 1 by 3 vector. All right, and similarly, I could do B transpose. B transpose is going to be equal to, was that 1, 2, 4, 7, 3, 9. Okay, that's B transpose. B transpose is a 2 by 3 matrix. All right, so pretty simple stuff. Now you could add, if something has, the same dimensions. So let's say A and A. Let's just do A plus A. you can add those because they're both 3 by 1. So a plus a, that's just going to be 2a, right? It's just going to be 2, 4, 6. Okay? Pretty simple stuff. Now, multiplying is a little bit of a different situation. So if you want to multiply two vectors or two matrices, basically you have to look at their dimensions and make sure that you can multiply. So we will multiply, let's say, let's say A transpose and B. Let's do that. So we're going to multiply A transpose, 1, 2, 3, by B, 1, 4, 3, 2, 7, 9. Okay? So when you're multiplying two matrices or vectors, this is again a 1 by 3 and this is a 3 by 2. The way you know you can multiply them is if these inside two numbers match. Okay? So we can multiply them because the 3 is the same as the 3. And the way that you multiply is you take whatever rows you have. This could be a full matrix, but you start with the top row, and you're just going to flip that up, and you're going to multiply. Let's imagine A is flipped up here. So we got the 1, 2, 3, right? You're just going to multiply all the numbers that are right next to each other. So 1 times 1, 2 times 4, 3 times 3. Okay, so we're going to do that. We're just going to flip this up and multiply it by this, and we'll get an element. And we're going to add all of these numbers together. So 1 times 1 is 1, all right? And 2 times 4 is 8, and 3 times 3 is 9. So 1 plus 8 plus 9 is 18. Yeah? So our first element is 18. Okay? And now we're going to do the same thing. We're flipping up this vector, and we're multiplying it by the second column. All right? So 1 times 2 is 2. 2 times 7 is 14, 3 times 9 is 27. So 27 plus 14 plus 2 is 43. Is that right? 43? Let's just say it's 43, whether it is or not. No, it doesn't matter. All right, and we're actually done, okay? So we ended up with a row vector, 18, 43. And how do we know that the dimensions on this are correct? Well, it's actually this first number and this last number, okay? So the inside numbers tell us that we can multiply them, and this number tell us what we end up with. So we ended up with a 1 by 2 vector / matrix, whatever you want to call it, okay? And the same principle would apply, let's say that, maybe this was actually a matrix, and it was a 2 by 3, and you had, let's just make it easy, 0, 1, 0, okay? So in that case, you would take this first row and you would multiply it out. You'd get the same result, but then you do the same thing with the second row. So 010 times this would get you 4, and times this would get you 7. So we'd get 4, 7, and you end up with a 2 by 2 matrix, okay? So that's how matrix multiplication works. Now, this, there's a special matrix right here, and whatever the dimensions are, where it just has 1s all along the diagonal like that. And we call this the identity matrix, or I, because the identity matrix, when you multiply by anything, you just get the same thing, okay? It's like multiplying by 1, all right, but in matrix form. So you might be interested in, what do I multiply a matrix by to get 1, basically, kind of like the inverse of a matrix, if you will. So to get the inverse of a matrix, there are different ways for higher row column matrices, but for now, all you need to know is a 2 by 2. So a 2 by 2 matrix, to get the inverse of it, basically you have some matrix that let's call it A, B, C, D, okay? And the inverse of the matrix is 1 over something called the determinant times your original matrix, but you're going to put negatives right here, and you're actually going to swap D and A. So this is a special way to get the inverse of a 2 by 2. Now the determinant is literally just AD minus BC. So you're taking the diagonals, multiplying them together, take the difference. So 1 over the determinant is 1 over AD minus BC times this matrix right here. You've swapped D and A, and you put negatives on B and C. This will give you the inverse of your matrix. If our matrix was called C, this would be C inverse. Okay? C inverse. All right, so that's how you get the inverse of a 2 by 2 matrix. And that might be it for matrices. What else do I want to say? I'll say that, okay, for a matrix to be symmetric, symmetric means that its transpose is the exact same thing as the original matrix. So clearly, you have to have a square matrix for this, because they're not going to be the same matrix if your matrix isn't square to start with. So let's say you have a 3 by 3, we'll give it a chance, and say you have 1, 2, 7, something like, you know, that, right? So here's your matrix, we'll call it D, and therefore D transpose would be if the rows and the columns were swapped, D transpose, and you would get the same matrix, right? Like if this column was a row, you'd get 1, 2, 7, and you'd get 2, 3, 4, and you get 7, 7, 4, 3, right? So because D transpose equals D, then D is symmetric. Okay? Idempotent, an idempotent matrix is a similar concept, but instead of D transpose equals D, it would be that D squared equals D. In other words, you multiply D by itself, and you literally just get the same matrix multiplying it by itself. Okay? So that's what idempotent means. You will notice that the identity matrix is symmetric, and it is also idempotent. You multiply 1 by 1, you get 1. Okay? So that's pretty cool. It's pretty cool. Talk about those concepts once or twice during the semester. Note that the order in which you multiply matrices matters. So if I have two matrices A and B, AB is not the same thing as BA. Those are saying totally different concepts. One of them might be valid, one of them might not be valid at all. And even if they were valid, they would probably not give the same result. Okay? So just keep that in mind. Keep in mind properties of transposes. A plus B transpose. You can just distribute that, A transpose plus B transpose. Nothing weird going on there. Product, transpose of a product, though, you do need to flip them. So you're going to do B transpose, A transpose is going to be the transpose of a product of matrices. Okay? That is all I want to say about that. Any questions? No questions. Okay. Let me just end with, forget it. Come to office hours if you want to see more stuff, but this, I don't want to deal with this board anymore. So hopefully that's helpful. See you guys.